So now, since we have got the adequate idea of what clustering is, which is actually in the domain of unsupervised learning, right? It is a technique in the domain of unsupervised learning, and now we already know that what is the ultimate goal of the clustering and what type of the data will we be having to cluster items. Obviously, we will have records, and each record will have various variables, but in this case the class label, which is available in the case of supervised learning, will not be available. So we will have to find heterogeneous groups in the data in an unsupervised manner, right? Although I have not touched supervised learning, but after we are done with clustering and its various algorithms, sorry, we will be going for the supervised learning as well. Right? Now, among we have multiple algorithms for sorting, as we had multiple algorithms for frequent asset mining. Similarly, we have got a list of algorithms which are there for the clustering methods. But one of the fundamental and commonly used as well, at times there are certain algorithms which are very fundamental. For example, in case of the association rules mining, the a priori algorithm is the fundamental algorithm or the basic algorithm, but a priori is not the commonly used algorithm in the domain of association rules mining because of obvious reasons, because of its exponential execution time. But in case of clustering, and specifically in the case of k-means clustering, k-means is not only one of the fundamental algorithm for clustering, but it is the most commonly used as well. Now, what it does is that the method involves choosing a number of clusters and then dividing the given n objects into k seeds randomly, right? So what actually happens is that you need to give this algorithm an input which is the number of clusters to be created. So this is the input which you are going to give to the algorithm, and this number of clusters to be represented to be created is represented by a variable k, right? And k can be any value greater than 1. I am not saying equal to, right? It should be greater than 1. For example, it should be 2, it should be 3, it should be 6, so on and so forth, right? So what does the algorithm do is that for a given data, for example, this is data and these are data points, and if you give this algorithm a value, let's say k is equal to 3, it will make 3 groups or clusters in your data, right? But if you give it a value, let's say k is equal to 2, what it will do, it will make two groups in your data, right? So this k-means, and later I will be telling you about k-medoids. Once you know k-medoid is a minor variation of k-means clustering algorithm. So this is input dependent, and you need to give the number of clusters to be extracted from the data beforehand, right? Then what it actually does within your data. Okay, let me show it visually. Within your data, for example, sorry, right, within your data, for example, these are various data points, and right, let me try to make a bigger sort of data, and then at present I'm using figures, but later I'll be showing you the actual data in the numerical form, numeric form with columns and rows. But for example, this is the data, and you say okay, k is equal to, let's say, 2. What it will do, first of all, it will select any 2 data points randomly. For example, it selects this data point, right, and for example it selects this data point randomly. It could have selected maybe this one or maybe this one, but since the choice is random, but it is dictated by the value of k, right. Now these points are called the seeds, right. These are the cluster centers, you can call it seeds, right. Then what happens is that what happens is that each and every data point is picked, and its distance from this center and its distance from this center is computed, right. Similarly, for the next data point, its distance will be computed from this seed, and its distance will be computed from this seed as well, right. And then for example, this data point is more near to this this one. Okay, let me number them as well. We call it S1, and let us call this S2, seed 1 and seed 2. Now since this this data point is near to this one, so it will be assigned to this cluster, right. Okay, for the sake of understanding, let me make all the data points in same cluster with green color, right. So, and since this data point is more near to S2, so it will be assigned to the cluster S2. Okay, let us make it blue, right. So this, so similar, I've given you example of these 2 data points, but the distance of each and every data point from the 2 cluster centers or seeds will be computed, and the seed will be assigned to one of the 2 clusters based upon the distance, right. So let me read it out so that I may not miss any point. The method involves choosing the number of clusters and then dividing the given n objects, choosing k seeds randomly as starting samples of these objects. Once the seeds have been specified, each member is assigned, each member, by each member we mean the each record in the data set is assigned a cluster that is closest to its based upon the cluster center based on the distance. Once the members have been allocated the mean value, now this one is important. Now once the members have been allocated, so within the cluster, this is maybe a cluster, maybe this is another cluster, and there are points, there are other points, right, and this point is the mean for the previous seed. This one was the previous seed, but once the cluster is formed, within this cluster average or mean of all the points will be computed that may result in a new point. Now this new point will become the new seed, right, and maybe here this okay, this another the other point becomes the new seed. Now once we have selected the new seeds, previous seeds will be discarded, and this previous seed will be discarded, and these new seeds will be used to recompute the distance of all the points and the allocation will be repeated, right? But maybe I've spoken this quickly. Later I'll be showing you the complete algorithm and the example as well, where you will have adequate idea how it works. Now, using the mean value for each cluster, the members are now reallocated to the cluster. As I earlier stated, in most situations, some members will change clusters unless the first guess is very good, right? Now this process repeats until there is no change in the cluster membership, and this is very important point, that the shape of the cluster or the clustering formation depends upon the choice of seeds which we initially make, which is a totally random choice. So if you have executed the k-means algorithm once, and for k is equal to 2, and again for k is equal to 2 you execute it again, you are most probably going to get different results, because the seeds both time will be different, because it is a random choice. Okay, right. So the algorithm basically tries to build clusters with high level of similarity within the cluster and with low level of similarity between different clusters, right? So this method requires means of the variables to be computed, right? Now this is the complete pseudocode, or you can say the list of steps which are there in the k-means clustering approach. So to start with, we select the number of clusters, and the number of clusters is stored in k. Then pick k seeds as centroids randomly. K seeds are picked as centroids, and these seeds are usually a random choice, but if you have domain knowledge, then you can manually or specifically pick certain points as well. Then the Euclidean distance is computed of each object in the data set from each of the centers, right? Now once we have computed the Euclidean distance, then each point is allocated to the nearest center based upon the distance. Once this is done, the computation of the centroids of the clusters is done by computing the mean of the attribute variables of objects in each cluster. Like once you have created clusters, then within the cluster, cluster heads are recomputed using the mean. Now finally we check if the stopping criteria has met, which means that the cluster heads have changed. If yes, then okay, we have to stop, otherwise we go back to step number 3, right? So it might be quite boring for you, so instead of explaining these textual points, let us straight away go to an example. Now here if you see, this is an example of a grade sheet, right? Okay, if we had an insight about the data, for example we say, okay, this is a very, let's say, talented student, and this is, for example, a very weak student, and if you want 2 clusters, so all the talented student will gather around this student, and the other weak students may gather around this one. So clustering may be formed in such a way, but here since we don't have the domain knowledge, so we will be picking cluster seeds or cluster heads randomly, right? For the sake of this example, I'll be giving colors to different clusters, and S1, S2 and S3, these will be selected as seeds for cluster 1, 2 and 3. Of course we are solving this problem for k is equal to 3, right? Now if you see here, the cluster 1 is, rather instead of now saying it's cluster 1 or 2, let me call them red, green and blue clusters, right. So what we have done is we have selected the 3 cluster heads or seeds, right. So if you see, this is second point, pick k clusters as centroid of the k seeds as centroid of the cluster, right. Now then what we will be doing is that we will be computing S4's distance from S1, S4's distance from S2 and S4's distance from S3, right. And whichever cluster head S4 is nearest to, we will be assigning S4 to that cluster. For example, if it is nearest to cluster 1, I will be assigning this one to cluster 1 and I will be changing its color as well. Same will happen for S5, 6, 7, 8, 9 and 10. Right? And to show you the influence or the effect of distance measure, I'll be computing the distance using Manhattan distance and Euclidean distance measures both, right. And you will see that how changing the distance measure changes the complete dynamics of the clustering. Now if you see here, you won't be able to understand it directly, so let me explain it to you. This S1 was our previous cluster head for red cluster, S2 for green cluster, S3 for blue cluster, right. Now S4, this is its these are the values of the instances. Now this column shows the distance of S4. This first number shows the distance of S4 from S1. The second number shows the distance of S4 from S2, and the third distance shows third number shows the distance of S4 from S3. Now if you see here that the minimum distance is 36, it means this S4 is closest to the cluster 3 or the blue cluster. So that is why we assign this record to cluster 3. Now this distance computation is based upon Manhattan distance, right. Using Euclidean distance, if you see the values, like Manhattan distance gave us 42 for distance between S1 and S4, but Euclidean distance is giving us 27, right. So the distance measure influences the results. Right. But generally for the instance S4 only, the Euclidean distance also suggests that this S4 should be placed in cluster 3. Right? Then the same goes for S5, and if you see the distances, the minimum distance is between S5 and cluster 2, so it is assigned to the cluster 2. Similarly S6, the minimum distance is between cluster 2 and S6 here, so this is assigned to cluster 2. Now this S7 is interesting. Here if we consider Manhattan distance, then the minimum distance is between S7 and cluster 3, but if we consider the Euclidean distance, then the minimum distance is between cluster 1 and S3, right. So this column is just made to or created to demonstrate you the influence of cluster distance measure, but otherwise you can simply ignore this one or maybe the other one, and you can use only one, because in any case you will be using only one distance measure, right. So now this is how these remaining data points are assigned to one of the clusters, right. Now, once we have created all the clusters, now if you see here that okay, 1, 2, 3, 3 data points are in red cluster, 1, 2, 3, 3 data points are in green cluster, and 1, 2, 3 based upon the Manhattan distance, 4 data points are in the blue clusters, right? Now this we have executed our k-means algorithm up till the point number 4, right? Now the next point is to find the mean of the next point is to obtain the new cluster centers, right? Initially we selected these cluster centers, but once every cluster has got its members, now it's time to compute new cluster members. So what we will do, we will be averaging out, like we will pick this instance, and this instance, right? And we will be taking an average of these 3 variables and putting it as a new value of age, and we will be picking these 3 values and taking its average, and this will be the average marks 1, and so on and so forth, right? So this is going to give us a new center for the cluster, right? And if you want to notice that the based upon Manhattan distance we are getting different centroids, we are getting different average values, and based upon Euclidean distance we are getting totally different values, and these values were the previous seeds, right? Now once we get the new cluster centers, we will be repeating this whole process, and instead of computing the distance from all instances to the previous cluster seed, now we will be computing the distance of each and every instance from C1, C2 and C3, right? So this is the next iteration where the distance of S1 is computed from C1, which is 8, and since this is the minimum as compared to the distance between S1 and C2 and S1 and C3, so this S1 is assigned to cluster C1. So and the same will be repeated for S2, S3, S4 and 5, right? And this process continues unless and until there is no change observed in the cluster centers. Okay. Now Euclidean distance is the default setting of the k-means, but you can, of course, you can change it, and there is no real definition of what metric is good metric as a distance metric between for computing distances, but one can try a number of matrices, right? Validation, once you have obtained the clusters, it's a challenging task, but in the previous lecture I already told you that there are cluster validity indices like DBI, DISC, Silhouette coefficient, Dunn index, Davis Boltin index. So these indices can be computed to verify the results, right? Now this is another visual example where initially these two groups were created, cluster centroids are there, and based upon the distance between the centers and the cluster points, clusters are formed. Later these cluster centroids are then updated and the new clustering is formed. So this is how k-means work. So the strength of the k-mean, which is a major strength of the its efficiency in terms of time, it takes order of t k n time, where n is the number of objects, k is the clusters, and t is the number of iterations, right? The weakness of this algorithm is that one of the major weaknesses is that it is unable to handle noise. Of course, for example, if you have data points like this, right, and there is another data point here, and these 2 points, okay, let me make them red. These 2 data points are outliers or noise. So, but since it has to compute distance from each and every point, so these points will also be included in the distance computation process. Ultimately, it will be influencing the result, and again, this since this is noise, so it may produce unacceptable results. So this is the weakness of k-means algorithm, but again, maybe we can use some pre-processing technique to eliminate the outliers beforehand, before going into the implementation of k-means. Another weakness of k-means is that it cannot discover non-convex clusters, right? So for example, now this is sort of convex cluster, right? But the non-convex cluster is, this is a non-convex cluster, right? So it cannot, and for obvious reasons, because there is only one center in each cluster, and it will try to make a circle around it or a spherical shape around it. So that is why it cannot make non-convex or non-spherical clusters. But there are other techniques which can do, which we will be doing later on in the course. Now coming to the k-medoids clustering, the k-medoids clustering is ditto same as k-means clustering, but instead of computing the mean here, which we have done, it computes the medoids, right? The advantage of k-medoid is that the cluster representative or the cluster center is a data point itself. It's not an imaginary point. For example, if you see here, these blue points are the data points, but these red points are not the data points, but they are center of the clusters, right? This is the k-means, but in case it was k-medoid clustering, the centroid of the cluster will be the data point, will be some data point itself, right? So this is how k-means and k-medoids clustering works. So this is sufficient for now. Thank you.